Okay, well, today we're going to look at issues associated with homework number 4, our last homework in our boot camp experience here in this class. And then we're going to go through chapter 3 in the textbook, which deals with some of the things that are especially related to the background statement that you're developing, um, which goes into the, I guess, the statement of the problem and the background statement, and then finally into the future, which is called the requirement specification that takes you very close to writing a proposal. So let's go here and start off with homework number 4. So basically, homework number 4 is repeating what you're doing in the homework number 3, where you're sequencing the 6 IMU accelerometer and gyro data streams, and you're streaming X and Z for 5 seconds and Y for 2, etc. The new thing is that you're going to be adding some external hardware. Now, this is not a Simulink switch. This is actually going to be an external hardware switch that you're going to push a button and you're going to change the stream from where it is currently to the next one. So let's take a look at the hardware. The hardware switch is right over here, and it's indicated by a signal input going into the Arduino. You can choose any of these inputs here. This one's going into input number 2. We're going to call it S. Going back to that diagram, if I'm in the state, sitting here for 5 seconds, lighting up the red light, or in your case, putting out the X stream, then as soon as I hit this switch, I go to the yellow condition where I'm changing over to the Y-axis, and then eventually if I hit the switch again, it'll take me here to the Z-axis, not as essentially, but it will right away switch me to the Z-axis. So the idea here, these are interrupts essentially that allow me to move from state to state right on top of the mechanism that you're using to stay here for 5 seconds, stay here for 2 seconds, and stay here for 5 seconds. Let's take a look at the switch designs that are possible. There's 2. Number 2 is one that's not the best. Here I'm going to, by the way, I've got 5 volts here. If you've got an Arduino Do, you may want to use 3.3. The switch can either be contacting the high voltage or ground. And in between there's an air gap, so it doesn't touch anything. So design number 2 is not so great. Design number 1 here is actually better. The switch output is connected essentially to the 5 volts or 3.3 volts through a resistor. And only when the switch is thrown is there a contact made, and then it grounds that out, and the resistor takes up the ballast between the high voltage and the ground. So let's identify where this is. If I hit my drawing pen here, I can see that this dot here is essentially this dot over here, and this through the resistor to 5 volts is this path here, and there's a resistor going to +5, which is on this column over here. Okay, in this case you might have to use again 3.3. And then where's the switch here? Well, here's ground, and so the switch would be, let's see, I draw an open circle here, and then the arm of the switch is this one, that's this part here, and then I would swing it to this, like this, and then it would make contact with that point. Okay, so this is the hardware design. Where did I get this? This came from actually the web reference here on the bottom. Now, the web reference actually describes another traffic switch controller problem, which is much more difficult than the one that we're addressing. So I don't want you to really look at this except to get this diagram here, because our diagram is much more simple than the one that they have. By the way, even on last week's homework, there's a preliminary set of states here that are used to check the X, Y, and Z, and you can get rid of that now that you've gone through the testing phase of the traffic light controller. Just stay with these 3 states and then insert this in your state diagram. Okay, so now this takes me to chapter 3. Chapter 3 is called Requirements Analysis. So it's talking a little bit about this section right here, but it does make mention of the statement of the problem. And so I'm going to, we're concentrating on the statement of the problem. or the background statement for Google form number 2. Back statement of the problem is Google form number 3. This is where you get started, Google form number 1, and then eventually Google form number 4, the requirement specification. So I'm going to basically center in on this section here, and then I'm going to talk a little bit about the requirement specification as we go to to that information. So let me get rid of this and continue on. So and the way I'm going to do this, I'm going to read some of the paragraphs as we go from slide to slide. It just makes it easier so I don't hem and haw. And I clipped this out of the book, so this should make it as basically as probably I only have maybe only 20% of what's in the book here. So I'm essentially giving you a speed reading through chapter 3. So one of the things we'd like to look at is this figure number 3.5, which illustrates some typical inputs that the engineer may need to consider, roughly categorized as enabling and constraining factors to a project. This is what you need to be talking to your sponsor about, and it reflects on your needs statement. So the primary input, as stated earlier, is the customer needs. Following is a brief list of other not-so-obvious factors which both enable the design or constrain it. So on this side are the enabling factors that help your design, and that includes getting experience either outside or in-house, other designs that have been done in the future, and, for example, some basic research. And let's get rid of this here to make the diagram a little bit bigger. Constraining factors, well, there's always financial limitations. There could be some legal restrictions such that somebody has a patent and you can't really develop this without doing some discussion with the person that has the patent. And then also your company might, that you're working for, might also want you to adhere to some existing designs, and you don't have free access to do whatever you want to do. So the needs assessment stating the problem is the center point of what we're dealing with right now. So you're dealing with a customer, and the customer's needs is your first responsibility or first opportunity to understand the requirements of the design. It is conducted with the customer and leads to a non-technical statement of the problem, and the design will attempt to solve. The problem statement, which is what you're working on right now, that's Google form number 3, but the background statement to that is Google form number 2, should exhibit the following attributes. First of all, you're going to be describing this in this area before you write the proposal in Google Forms 2 and 3, basically as in a non-technical manner. Also, you're not going to quantify a lot of things like dimensions, quantities, and costs. But nevertheless, as I indicate here on these bottom 2 points, it really needs to be complete as possible. The problem statement should cover all the aspects that the designer anticipates encountering during the design. It also should be specifiable. Although the problem statement is more subjective, in the end it should align with a more detailed and quantitative requirement specification. Basically, this will lead into that requirement specification. Now, when you're dealing with the customer, there's always a tug and pull between determining what the essential needs are and the customer has their wants. And so determining needs through questioning the customer is neither simple nor straightforward in many cases. It involves an interactive process of questioning and re-questioning, always attempting to seek out as many varying opinions as possible. An important skill is the ability to differentiate a project need versus project wants. So this diagram here is indicating that you have some true needs, which are in regions A and B, and B is actually part of C, and the C is indicating a region where the customer has a certain amount of wants. Some of these are outside region B, such as shown on the next diagram. So what really is the job of the engineer is to translate those customer wants into a problem statement that reflects the true needs. So you can see that we are moving this diagram into the true needs. Now, this diagram is also indicating that maybe those true needs are, some of it is actually outside of this. So neither you nor the customer actually have found out that there are some needs that need to be inside this. And what needs to be inside is this dotted box. Okay, so inside that dotted box are the needs as reflected in the problem statement. So the problem statement probably needs to be increased and move that problem statement out to incorporate everything, including the true needs, not the wants, but the true needs of the project. Remember, the true needs is this dark gray area consisting of these three sections here. So something to think about when you're talking to your customer. Also, your project will have certain boundaries. And these are sort of external factors which will limit the alternate solutions that the engineer can consider when doing a design. Exploring the boundaries of a project is an effective way of determining needs. These needs are, again, in your needs statement. So common boundaries of a project that needs to be investigated is basically capacity limits. You may be asked to design something that's just plainly too big for you to handle. Another factor could be that your company has certain operation standards and methods, and you need to fit your work within that, or your company's not going to be happy with. And then there's also legal boundaries to contend with, such as you cannot do this because another company has already done it or has rights to it. This diagram is kind of referring to the idea of conceptualization. It's called input-output analysis, and stating the design problem is also often assisted by conceptualizing the design as a functional block that receives inputs and delivers outputs. Remember Rob Sullivan and his box for a guitar tuner and his LEDs, and he drew that out. So this conceptualization forces the engineer to consider what the design is to do and thereby establishes and clarified needs. So this example is actually from an agricultural sprayer controller. I really don't want to get into the details here of this, but they've got some user inputs here on this side, some sensor inputs over here, and then some outputs over here. So basically it's a diagram that indicates the inputs and the outputs like Rob Sullivan did. Okay, so there's also a number of attributes that are common to most designs. Surveying them and assessing them, their relevance in the design problem will help expose needs. While doing this, it's helpful to categorize attributes as either functional or non-functional. Categorizing attributes in this way forces the engineer to think about what a design, number one, must do, those are functional attributes, and what a design must be, which are non-functional attributes. So we understand what a functional attribute of a cell phone is, and so actually a new cell phone design would have to look at different functions and compare itself with others by maybe looking at standard functions that it executes and advanced functions that might be in the design coming up that you need to put in. Non-functional attributes, including things like user interface, packaging, battery, production, reliability, and surface. Those are all important things, but they're really not functional. They're just something that needs to be done. Now, this example with the functional attributes and the non-functional attributes, we're going to explore on several of the next slides, looking at how to weigh these factors in certain ways. So, for example, in a cellular telephone design, that it really illustrates conflicts that can often arise between functional and non-functional needs, as we'll see here. The packaging, for example, may call for a small size. Like everybody wants a small cell phone, yet the power requirements may demand that it has a large battery. So this conflict may be unresolvable unless improved battery technology is developed, which may also be in conflict with other factors such as cost, which is and design time expectation. So on this diagram here, it only has the small size and the power requirements, but there's a couple other factors that are also illustrated, like high quality look and high tech display. So maybe these two are functional and these are two maybe non-functional, roughly speaking. So if we look at the description here between small size and power requirements, bringing up my pen again, then I would say in order to satisfy small size and power requirements, I have to be in this region here. Okay. However, if I consider high quality look and high tech display, then I'm limited even further. For example, maybe to satisfy all four of these, I'd have to be in this region here. Okay, so this is the idea behind that. Okay, so on this diagram, expanding back out here, is that we could spot possible conflicts between size, battery capacity, display appearance, and range by developing a matrix. So this matrix is basically illustrating some strong correlation, medium correlation, and even negative correlation between these different factors. For example, we just mentioned size and battery capacity. That has a strong correlation that's indicated by the double plus. Battery capacity and display has only a smaller amount of correlation, and display and range has negative correlation, indicating that would be weighed in the negative manner. So that's a kind of chart that you can develop, or a matrix. So this diagram here is indicating, again, I'm concentrating on doing the statement of the problem here, but we're looking in the future to do a requirement specification. And so let's look at the next few slides and see how it deals with the statement of the problem, indicating that eventually we'll have to come up with this last diagram here on this chart. And the main idea here is that a good statement of the problem will be both complete and consistent, that will help develop our future requirement specification. So some things that we'll be looking at in the future is searching out expert sources that would help us more with a more detailed requirement specification. We also may have to analyze similar designs in that scenario, and eventually conduct some tests or experiments. In our case, it'll be computer simulations. Remember how Rob Sullivan actually set up a guitar and a microphone to get some firsthand knowledge of how things might work. Now, something that you want to do is keep this in mind, that some requirements, if they're excessive, can actually degrade your project and your design. So for example, here on this chart here, we're indicating how costs are rising for a project. Typically, you always think as you're adding more features, things would go linearly. Here in this chart, it's indicating that you have an exponential change. So you got to be careful about adding too many functions or features, which I call excessive, and keeping it reasonable so your design costs don't go up too fast. Also, it's possible that in this example here, showing a jump in the curve between reliability and cost. So you would expect that cost goes up linearly with reliability, and here it's indicating that it's not that at all. So you got to be careful about that. Really stringent or conservative specifications can dramatically increase the design costs. My last slide here is indicating something that you'll be doing on the requirements spec, which is something called a systems test. So let's just go read this. Eventually, it will be necessary to verify whether or not a design fulfills the needs of the customer. Again, remember the word needs. So this is related to the thing that you're working on, of the customer, as stated in the requirement specification or even in your background statement. This is accomplished through a system test, often referred to as the acceptance test. So basically it says this: are your tires good? Well, let's see how good they are. And we're going to run them and see how long they can last under stringent considerations. So this is where we're going to leave off for today. I hope you've got something out of Chapter 3. We did the whole chapter in just maybe 20 minutes, which is plenty fast enough. And we'll return back to this subject going into Chapter 4 at a future time.